In Chapter 8, Section 3, we're going to be looking at the graphs of the quadratic functions. This is not something we spent a whole lot of time doing this term in this course, but it's about time we take a closer look at graphing, because we can get a lot of information and can solve a lot of problems by looking at the models created by quadratic functions and then what their graphs look like. In fact, in most of the graphing that you will have done in your courses, with the exception of graphing linear equations, the standard approach has always been to just construct a table of values. You have an equation that depends on x and y, so you build a column for an x, a column for your y. You choose values of x, you plug them in and solve for values of y, and if you get enough of those points, you can approximate what the shape of the curve looks like. The fundamental flaw in that is that there's never enough points to know for sure what's going on. And so we're going to take a little bit different of approach. The approach we're going to use in now Section 3 of Chapter 8 is to have some fundamental knowledge about the types of curves or the types of equations that we're working with. In this case, we're going to know ahead of time exactly what the shape of the curve is. We're just going to determine where it shows up on the graph and exactly how wide or narrow it is. The name of the curve for the quadratic function is the parabola. So let's take a closer look at the parabola, how we determine what the graph of the parabola looks like, and then how we might use that to answer some questions where the real world might be modeled by a quadratic function. Let's start by talking about how we recognize the characteristic of the parabolas. Now, by definition, the graph of the quadratic equation given by ax squared plus bx plus c is called a parabola. Now, the basic shape of a parabola is this U or cup-like shape. Sorry, let me if I can try to get my graphs as accurate as possible. So, say on a plane you have a parabola may look something like this. A parabola can be narrower than that. Still has that basic U shape. Or you can even have a parabola that looks like a downward parabola. Okay? Or a downward parabola that's narrower. These are all examples of the parabolic shape. By the way, I just discovered in my little note drawing utility the ability to draw these axes on there. So sorry that it's been long time coming of getting my axes to be as straight as what I've got drawn here. Okay, now some important parts of the parabola. The vertex or turning point is the lowest point of the parabola when it's an up parabola, and it's the highest point on the parabola when it's opening downward. Right? So it's the turning point. The vertex is where the parabola changes direction. So that's what we mean in all of those cases. The dots that I have drawn are the vertex. Okay? Now, every parabola is symmetric about a vertical axis passing through the vertex. Looking at these graphs right here, what you'll see is right down this line. Well, that's not going to work. Let's try that again. Let's try this again. Right down the line here in the middle, there is your axis of symmetry, right? It's a vertical axis, goes right through the vertex, and it's the same on either side of the graph. Okay? You get the picture? Oh, let's try this one more time. The vertical axis goes right through there. There's your axis of symmetry. And on the last one, you also see, actually, the axis of symmetry in this case is the same as your y-axis. Okay? So that's your what's again called the axis of symmetry. I write it in green. That's the green line that I drew on each of those examples. I want to demonstrate for you now by actually using value tables so you can see what the shape of the parabola looks like in terms of its points. So let's look at these three different graphs. Okay, I'm going to graph this one in red. I'm going to graph the second one here in blue. I'm going to graph the last one in a green. Okay, so let's use a value table to construct what this graph would look like. Okay, so I'm going to put an x column. I'm going to put an x squared column for my f function. I'm going to put a 2x squared column for my g function. I'm going to put a 1/2 x squared column for my h function. Okay. What I'm going to do is I'm going to pick a series of values for x and plug them in and see what the height of these curves each look like. All right. So let's look at -3, -2, -1, 0, 1, 2, and 3. Let's start by looking at x squared. So if I take -3 and square it, I'm going to get a +9. If I take -2 and square it, I get a +4. If I take -1 and square it, I get a +1, 0, and then 1, 4, and 9. So let's put this as 1, 2, 3 here. -1, -2, -3. Let's go up a height of let's say 1, 2, 5, 6, 7, 8, 9. So right there is my height of 9. So for the red curve, it's at a point 0, 0, right here. I know at -1 it's a height of 1, at -2 it's at a height of 4, and at -3 it's at a height of 9. And same thing's going on in the other direction, at a height of 4 at 2. Right there. And so let's draw this curve. This is the shape of the curve going through those points. Okay, same thing this direction. Alright, so that's y is equal to x squared. Now what happens if I do 2x squared? Put a 2 out in front. Okay, my numbers will be larger now. This is going to be 18 because you take -3 squared, you get 9 times 2 is 18. It's twice what this column is. So 8, 2, 0, 2, 8, and 18. Now 18 is too large, but I can do the other two. It's at a height, actually notice 0, 0 is still on this curve as well. It's at a height of 2 when I go over 1. If I go over 1 over 2, right, +2, I'm at a height of 8. And if I went over 3, I'm way up here at a height of 18, right? And the other direction, I have -1, 2, I have a -2 and a height of 8, and I have another point way up here. Alright, so here's what this curve looks like. Notice it's still got the same characteristic U shape, it's only steeper than the last curve was. Okay. Now what happens if I put a coefficient of 1/2 out in front of the x squared term? Well, I'll have half of 9, which is actually 4.5. I'll have a 2, a 0.5, a 0, a 0.5, a 4, not a 4, sorry, a 2, and a 4.5. Again, all I'm doing is taking the x number and plugging it into this function. -3 squared is 9, times a half is 4.5. So graphing -3 at a height of 4.5 is right about here. -2 at a height of 2 is right here. -1 at a height of 1/2. Notice it's still at 0, 0, 1/2. The curve is just half as high in each case. Still got the same characteristic U shape. So you can see what effect that number out in front has on it. It determines the height. Now what would happen if I were to put a negative sign out in front? The effect of the negative sign will be so that each one of these points, instead of being positive, would be negative. It turns your parabola upside down. Okay, so here's what we're going to do, is we're going to use this information to help us construct our parabolas without actually having to go through the value table every single time. We're going to know that the A, the number that's out in front of the x term, tells us something. One, it tells us how steep the parabola is. The higher the A, the narrower or steeper the parabola is. And the lower the A, meaning the closer to 0, the flatter the parabola is going to be. And then if we put a negative sign in front of it, it's going to tell us if it's down, and if it's positive, it's going to be up. Okay, so that's kind of the model we're going to be working with here. Let's take a look at some more. Now there's one form that the parabola can actually show up in that will give us actually all the information that we need, probably all at once. It's when it's in this form right here. Now notice this is not ax squared plus bx plus c, but this is in a factored form, which we call the vertex form, or just an alternate form for the parabola. When it's in this form, when you see it factored like this, and you see a times the quantity x minus h squared plus k, where a, h, and k will be specific values, you can use this to graph, right? What you know from this is that the number out in front, the a, is what tells you whether it opens up or down. If a is positive, it opens up. If a is negative, it opens down. If a is large, that is the absolute value of a is large, then the parabola is narrow, right? Very skinny. As opposed to if it's nearer to 0, like 1/2 or 1/4, or the closer to 0 it gets, it's very wide, right? In this sort of shape. Okay? The vertex of the parabola, the turning point, we actually know where it is. It's given by the h and the k. Okay? Now there's a negative sign built in, so it's going to be the opposite of whatever sign you see inside the square, but the x coordinate is h and the y coordinate is k. That is the location on the graph of the turning point. And finally, the axis of symmetry for this parabola, the vertical line, is given by the equation x is equal to h. So here's what we do. If we want to graph this quadratic function and it's in this form, we first determine if it opens up or down. Again, recalling from up here, if a is positive, it's up. If a is negative, it's down. That's the number out in front of the square. Then we determine the vertex of the parabola. We just identify what the h and the k are. Then we find any x-intercepts, so we know where it crosses the x-axis. That's what you do by setting y is equal to 0. You can also find any y-intercepts by setting x equal to 0. Okay, really the most important steps here are 1, 2, and 4. 3 is kind of optional, meaning that if you have enough information from the first, for the 1, 2, and 4 to graph this curve, then you can stop there. Sometimes, however, if you don't have enough information there, for example, if it crosses the vertex and the y-intercept are the same point, or the vertex is on the y-axis, you may need extra points to make sure that you can see what the parabola looks like. You'll be able to determine whether or not you have enough information by graphing this when we get some examples. Okay, then you plot all those intercepts and the vertex and any additional points that may be necessary to determine the shape of the parabola. But mainly what you need is whether it's up or down, the vertex, and then some intercepts. And whenever you get these things plotted, you're going to connect the points that you've plotted with a smooth curve, right? That's shaped like the parabola. So it needs to be some smooth curve. Now let's look at this thing. Let's identify, first of all, whether or not this thing is up or down. Okay, is this an up or down parabola in this example right here? Well, notice right here, A is -1. So what does that mean? It means it's a down parabola, right? A is -1. So first thing we know is that on our graph, let me put some axes here for us. My x-axis, and I'll draw my y-axis. I know it's going to be going downward shape. Now I have no idea where this thing is or what the shape is, so I've got to move on to the next question, which is what's the vertex? And the vertex comes from right here and right here. Okay? Now, the h is always the opposite sign because remember in the formula, I'll scroll up so you can see it, there's a minus sign already there, right? So the h is what is here without the minus sign. So it's the opposite sign there. You see a -1, but the h is going to be 1. And k is just straight out of there because there's no minus sign in the k. So it's 4. Okay, inside, take the opposite sign. Outside the square, you just take the number that's there. So at 1, 4, if I go over 1 and up 4, this point right here is my vertex. Now I know it goes down from there. So the question I'm going to ask now is, where does this thing cross the axis? So let's do the y-intercept first. Y-intercept. That is, where does it cross the y-axis? And remember, from up here, to find that, you set x equals 0, right? You're going to plug in x is 0 to find where it crosses the y-axis. So f of 0 would be negative 0 minus 1 squared plus 4, right? Is minus 1 squared plus 4 gives me minus a positive 1, so minus 1 plus 4, or 3. Okay, which makes sense. That says it's going to be right there. Now notice, because this thing is symmetric, I also know that there's another point right here. Okay, so I know the curve looks something like this. Now the question next I want to know is, where does it cross the x-axis? So what I'm going to do to figure that out is, number 3, I'm going to set y equals 0. That is, I'm going to set the whole thing equal to 0. Negative x minus 1 squared plus 4 equals 0, and solve that. Okay, now this is a quadratic equation to solve, so I start by multiplying out the x minus 1 squared. Right, I have x, remember, by the way, I got to come off to the side and do this. X minus 1 squared is the same thing as x minus 1 times x minus 1. So x minus 1 times x minus 1, you have to FOIL, or monkey face, to get the expanded form. So I end up with minus 2x plus 1 plus 4. All of this is still equal to 0. Okay, simplify that. I have a minus x squared minus 2x minus 1 plus 4 equals 0. I'm running out of space. I'm going to come up here and work the rest of the way. All right, so I have minus x squared minus 2x plus 3 equals 0. I'm going to divide everything by negative 1 so that I can factor this thing easily. You could just use the quadratic formula, but I think this thing factors very easily. So if I get the first term positive, it makes it very easy to factor. Right? This becomes x plus 3 minus 1, which means I get x is equal to negative 3 and positive 1. So over here at negative 3, I think I've got this backwards. This should have been a positive, so this becomes positive. That makes this negative. So this is minus and this is plus. Sorry, so that's plus and minus. I'm over here at positive 3 is where I cross, and at negative 1, right, which is very consistent with the shape of the curve that I've got right there. There's my parabola. Okay? I kind of got a little sidetracked down here, but you understand what I'm doing. All I'm doing is finding first, whether it's up or down, finding the vertex, plotting. Now, let's do this. Okay, I'm going to take a second. We're going to go over to course compass, and I'm going to show you an example of how you draw this parabola, because in course compass, you actually only need 2 points to draw the parabola. 2 points. Okay, once you have 2 points, you can draw the parabola in your homework, which means the work that I did down here on number 3 is actually extra, and you won't have to do that on your own. I just wanted to show you where they were explicitly on the graph. Okay? Here we are in course compass in a very similar question that we just did. It says, use the vertex and intercepts to sketch the graph of the quadratic function. Okay, now in this case, notice the A is 1, right? So we know this is an up parabola. Now where is the vertex of this parabola? Okay, now I'm not going to be able to write this on the screen, but let me explain it to you. This right here, remember, you take the opposite that you see there. It's negative 1, so the h is going to be positive 1. So my x-coordinate is positive 1. My y is negative 4, so it's going to be down here at 1 comma negative 4. Okay, I need to plot a point right there, but I want to plot a parabola, so I look at this and I say, okay, which of these tools am I going to use? Well, this is an up or down parabola, so I can use the vertical parabola tool. If I click it, I come down here and it gives me these crosshairs, so I can go and plot where that's going to be. The other thing I want to know is, what is the y-intercept? Okay? So let's take a look real quick. I do need to write on the screen here, so let's look at the y-intercept. Zoom out a little bit here. We've got in this problem right here, let me write on the screen, that the vertex, we've already identified that A is 1. The vertex here, H is 1, K is -4. So we're going to be at this point right here. We'll come back and graph it in just a second. Now what about the y-intercept? So you let x equal 0. What do you get? F of 0 is 0 minus 1 squared minus 4. So that's -1 squared minus 4. 1 minus 4 is -3, right? So -3 is going to be right here, is where it crosses the y-axis, right? Okay. Now I'm here on a screen copy, so I'm able to write on the screen. Let me go back to the actual web page window. So there it is, -1, 4, and then the other point was -3, 0. Okay, I just clicked at 1, -4. Sorry, I said -1. 1, -4, and then at -3 was the y-intercept. Okay? Now, the question, is that correct? Fantastic. Do you understand? So you only need 2 points to graph this thing. Hope that helps. Now that we've done one like this, we can do this one relatively quickly. Again, A is 1, so that's going to be an up parabola. The vertex is going to be 2, 1, right? K is equal to +1. What about the y-intercept? Let x equal 0. That gives us that f of 0 is 0 minus 2 squared plus 1, or -2 squared plus 1, which is 4 plus 1, which is 5. That's where it crosses the y-axis. Okay, so drawing our axes here. Our vertex is at 2 and up 1. It is an up parabola, which makes sense that then that the y-intercept is going to be here at 5. So my graph goes up through that point, and also would go up a height of 5 and over 2 this way because it's symmetric. And there's the graph. Okay. On the homework, you only need the 2 point. On the homework online, you need 2 points. When you're graphing these things by hand on your test, which you will be required to do at the proctored exam, make sure you know how to graph the picture by hand. So be able to draw these lines and plot this thing actually on the tool. You might want to do a little practice of that. Now, the most pertinent question at this point is, what if it's not in that form? What if it's not in a times x minus h squared plus k form? What if it's ax squared plus bx plus c? Well, the nice thing here is that we've got a quick and easy little formula that will get us the vertex, which means we can answer all the same questions in exactly the same way. If f of x is equal to ax squared plus bx plus c, the vertex is, okay, and here's the formula you got to remember. The x-coordinate is -b over 2a. Okay, b and a coming from the form that the equation is in. And then to find the y-coordinate, you just plug that in. -b over 2a. Once you get that x, you plug that in for x here and here, and then work out what that value is going to be. And the axis of symmetry is the line that goes through -b over 2a, a vertical line through x equals -b over 2a. Okay, so you're going to need to know this. In fact, this is the big thing that you've got to remember out of this section. -b over 2a. That tells you the vertex when you're in ax squared plus bx plus c. -b over 2a. That's a formula you need to remember. Okay, so for this example here, you start by finding out the a. Tells you whether it's up or down. A in this case is -1, so this is going to be a down parabola. Next thing you look for is the vertex. Okay, now there's no h and k in this form, so you're going to use x is equal to -b over 2a. That gives you -4 over 2 times -1, because the b is 4 and the a is -1, so you have -4 over -2, which is +2. Now how do you find the y part of the vertex? You plug the 2 back in. Plug the 2 into the equation. F of 2. which is going to give me a negative 2 squared plus 4 times 2 plus 1. So that's negative 4 plus 8 plus 1. Negative 4 plus 8 is 4, plus 1 is 5. So your vertex is the point 2, 5. Okay. Lastly, you find your y-intercept by letting x equal 0. So f of 0 is plugging 0 up here in for x. You have negative 0 squared plus 4 times 0 plus 1 gives me just 1. So 0, 1 is my y-intercept. Now let's graph those points and see if we have enough to determine exactly what curve we're looking at. Okay, so the vertex is at 2, 5, so over 2 and up 5. It's a down parabola. My y-intercept is 0, 1, so it's going to go, it goes over 2 and down 5. So over 2 and down 5 in this direction. It's symmetric. There is my parabola. Okay? There are a couple of nice applications for quadratic functions now that we know what the shape of their graphs are. Because the vertex is this turning point, we can, if we have a model that is a quadratic equation model, that is the graph of the model formula is a parabola, then we have either a maximum or minimum value to the quadratic function. If it's an up parabola, we'll have a lowest value. So imagine that your profit, no, not profit, profit's not a good one, cost, the cost for your business is a quadratic function, and it turns out to be an up parabola. You are interested in finding out what is the minimum cost for my business. What is the minimum cost it's going to put together? If cost is in terms of the number of objects that I make, you've got fixed costs like rent and facilities. You've got variable costs that depend on how many objects you make. If you're a shoe maker and you're a golf club maker, you got these costs that are fixed no matter how many golf clubs you make, and then costs that depend on how many of them that you make. If you can find a way to optimize how many you should produce in such a way that you minimize your cost, that's an interesting thing for you. You want to know that kind of information. Or say you've got a profit function based on how many you are able to sell. Your profit depends on things like what price you set your commodity at. It depends on advertising budgets and things like this. If you want to be able to maximize your profit, if it turns out to be a quadratic formula, we know what that value is. It turns out to be the vertex. So the maximum minimum of quadratic functions is what we're going to be looking at here. If a is positive, then f has a minimum that occurs at the vertex, namely, since we have a formula for it, pardon me, I can spell minimum while I'm talking at the same time. That would really help out a little bit. Minimum that occurs at x is equal to negative b over 2a. And the minimum value is whatever you get when you plug that into the function. If a is negative, that is it's down, then f has a maximum value. And it occurs at x is equal to negative b over 2a. And the maximum value is, again, the function value when you plug that in. So when you're in this chapter and when you have a quadratic model, a quadratic equation, if you're asked for a maximum or minimum, just think vertex. Maximum, minimum, they're just asking for the vertex. So it's the same formula you used to find the vertex before. In this example, a person is standing close to the edge of a 200-foot building and throws a baseball vertically upward. We've got the building here, person standing up on top. They're going to throw the ball upward and it's going to follow some trajectory. Notice how that shape tends to look parabolic. If you think about how that thing's going to fall, we know that the height is 200 feet. We're given a function. This function right here tells us how high the ball is given t seconds after he's thrown it. The question that's being asked is, when does the ball reach its maximum height? And what is the maximum height? Okay, so after how many seconds does the ball reach the maximum height, and what is the maximum height? That word maximum is the clue, right? Pay attention to that. That gives you the clue, the key word that tells you we're going to be looking for the vertex. So we're going to use negative b over 2a to find that, right? In our case, that's going to be negative 64 over 2 times negative 16. Okay, negative 64 over negative 32 is 2, which means after 2 seconds, it reaches the max. Now, how high is that maximum? Well, since we have a function that tells us how high the ball is at any time, we're just going to plug the 2 in for t to figure out how high it is at that point. Plus 64 times 2 plus 200. So negative 16 times 4 is negative 64. Plus 64 times 2, that's 128 plus 200. That gives me negative 64 plus 128 is 64 plus 200 is 264. That is the maximum height, which makes sense. It's above 200, right? Which tells us that this total height right here is 264. Okay, that's consistent. Those are my two answers to that first question. Now the second question, part B, says when does it hit the ground? That's not a maximum or minimum question. They're just saying when does it hit the ground. Now what is the height of the ball when it hits the ground? Right? What is the height down here? 0, right? The height of the ball when it hits the ground is 0 feet above the ground. So the question is, when does s of t equal 0? So all we got to do is take negative 16t squared plus 64t plus 200, set it equal to 0, and solve for t. Right? That's easy enough. That makes sense, right? It's a quadratic function. How do we solve quadratic equations? We use the quadratic formula. We use complete the square, or we factor if we can. Now these numbers are big enough that I don't want to factor or complete the square. So what I'm going to do is I'm just going to plug this into the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now I'm going to head out to my calculator and get some of these numbers done. Negative 64 plus or minus the square root of 16,896 divided by negative 32, okay, which is going to be negative 64 plus or minus 129.98 divided by negative 32. Now I think if I do the plus, I end up with a negative answer overall. So it's going to be the negative here that gives me the right answer. 64 negative minus a 129.98, and then you take 32 and divide by it, negative. I ended up with 6.06 seconds. Okay, or roughly 6.1. I think it says round to the nearest tenth of a second. So 6.1 seconds is the final answer. All coming straight out of the quadratic formula then. So we need to find s of 0 in this example. Now s of 0, that's pretty easy. That's negative 16 times 0 squared plus, it was 64 times 0 plus 200, which gives me just 200. Now what does that mean? Think about what the function meant. The function meant the height at time t equals however many seconds have gone by. 0 would mean at the very beginning, right? So that's the height of the building. So that's consistent, right, that with what we've discussed. And now the last thing we want to do is graph the results on a graph so we can see exactly what's going on. This is where you see the value of being able to graph a function like this. You actually can see a graphical picture of what's going on in that function. So let's say this is a height of 200 here. Let's say that's 264. So we know we start here at time equals 0. At how many seconds? It was 2 seconds that went by. We were at our maximum height. Then a little bit after 6 seconds, 3, 4, 5, 6, 7, here's 6, right about there, we end up at the lowest point. So this is my vertex, and then my curve looks something like this. There we go. Last question. We're ready for our last question now. You have 600 feet of fencing to enclose a rectangular plot that borders on a river. If you do not fence along the side with the river, find the length and width of the plot that will maximize the area. What is the largest area that we can enclose? So let's draw a picture of what we have here. We have the river right here, and we're going to build a fence along that river coming out this way, and it's going to be a rectangular plot. And we have 600 feet of fencing available. The question is, what's the maximum size of an area that I can enclose? Say I'm going to use this for grazing. I want the most possible area here. Now if I spread it out too far, that it might be too thin and not get much area. If I do it too wide away, still using 600 feet of fencing, there's a good balance, right, where we have the most possible area enclosed. So the question is, what is that most possible area that we can do it? Okay. So here's what we've got to do. We've got to set up an equation that models the amount of fencing that we're using, that models the area, actually, is what we want to model because that's what we want to maximize. So how do you find the area of a rectangle? Remember, the area of a rectangle is always length times width. So we need to identify what the length and the width are going to be in this case. So let's say we don't know what the width is. In both cases, the x is going to represent the width since it's the same on both sides. How long is this side? Now we could use another variable, but that doesn't help us here. What we are going to use is how much fencing we have to finish this off. Now if I've used x feet of my fencing here and x feet of my fencing here, I'm going to be left with however much total I have minus how much I've used, which I've used 2 of my x, right? So what's the area now that I have this written as an expression? Well, it's still length times width. My area is going to be 600 minus 2x times its width, x, or 600 minus 2x squared, or if I write it in standard form, negative 2x squared plus 600. X, sorry, should be an x here, plus 600x. There's my area. Now I want to maximize this. Remember, I told you, whenever you hear the word maximize, what that always says is use the vertex, because this is a quadratic equation. It's a quadratic function, right? So maximize means find the vertex. How do we find the vertex? We use negative b over 2a. That's where the vertex occurs for a quadratic equation, quadratic function. So in our case, negative b would be negative 600 over 2 times negative 2. It's negative 600 over negative 4. 600 divided by negative 4 is 150. So that says that my maximum area will occur when my value of x is 150, right? So that's the width. Now what's the length? How do I find the length? Well, use this. 600 minus 2 times 150. 600 minus 300 is 300. So it is 300 wide, 300 feet wide, and 150 long, or 350 long, 150 wide. And what's the area? It does ask us for that as well. We'll just take 300 times 150. Length times width is the area. That's going to give me 45,000 square feet. And there we go. That's the end of Section 3 in Chapter 8, using graphing and vertexes to answer questions about quadratic functions.